Hello, everybody. We are just getting people joining the webinar, and we will start in a minute. Welcome, everybody, by the way, and thank you for joining us. Okay, we have 50 participants so far. We had quite a good number of people registered, so let's wait a little bit. Okay, one more minute and we start. Okay, I think that is starting to stabilize the number of participants joining. So given the constraints, obviously, of time constraints of the webinar, we have just 1 hour. It's better if we start off the event. So as I said, welcome to the webinar. Thank you very much for joining us, for registering and joining us. And as you know, this is the third webinar on STEAM and healthcare. The first two ones were on sensor technologies in healthcare, the second one on cybersecurity. And today we are running this webinar on artificial intelligence and healthcare with three very good speakers, obviously, that are familiar with this area. So we'll proceed as follows. We have first Constantino Carlos Reyes Aldasoro from the Department of Computer Science. Then we have Cristina Malamateniu from the School of Health Sciences at City University London as well. And finally, Giacomo Tarroni from the Department of Computer Science and the Center for Artificial Intelligence. And just will be chairing the event. I am Dr. Eduardo Alonso. I'm the Director of the Artificial Intelligence Research Center at City University London and the chair of this webinar. What I would be ask the participants is, please, if you have any questions during the sessions, just post them in the question and answer button, at the bottom of your screen. And the participants will be answering the questions at the end of all the presentations. So we'll have 15 minutes for each of them, and then 15 minutes to close the event. And it's then when they will be answering your questions. So without further ado, again, welcome. Thank you for joining. And Carlos, the floor is yours.
Thank you very much, Eduardo, and welcome to everyone here to this webinar in healthcare. And today I'm going to be talking about analysis of cancer cells, and we're talking about artificial intelligence, but I want to highlight that we also can use human intelligence, so we shouldn't just forget that we can also use this. So I'll be talking about cancer cells, and these are some of the examples of the cancer we'll be analyzing. But first, let's talk a little bit about cancer. So to give an introduction to everyone, cancer is a very common disease. We all know, and we all may have experienced someone close to us that would have suffered cancer. And cancer actually is not just one disease. It's a group of many diseases that share some characteristics. And they all start with one cell whose DNA goes wrong, and then there'll be some changes in the DNA, and then this cell would not follow the normal process of a normal cell. So there are some hallmarks of cancer, and the cell would not die at a certain time, and they would reproduce uncontrollably, and then they start growing, and they create tumors, and then they can escape and form metastases. So this is common, and it is estimated that now 1 in 2 people will be contracting cancer during their lifetime. So chances are that most of us would have it, or at least some of us will have it. And it's very common since a long time ago. So there are Egyptian mummies that have been diagnosed and they have been found to have tumors. And it's not the biggest killer. The biggest killer in the world is still cardiovascular diseases, although that is decreasing considerably, especially due to less smoking. But cancer is very important in that. Now, what I want to highlight here is that approximately 1 in 6 people will die of cancer, but approximately 1 in 2 people will contract cancer. And this is important because 1 in 2 will contract it, but then 1 in 6 will die. And why is that? Why is not everyone who contracts cancer dying of cancer? Well, that is thanks to a lot of research that's been carried out in this area. So many people carry out research in cancer, including myself and many other people. And we are trying to contribute with different cures. So there are many ways to treat cancer. So there are some cancers that will never develop into something harmful, and then they will just go away, or they will be contained. But then there are other ways of treating it. So surgery can be removed. It can go through chemotherapy. So some chemicals will be used, or it can be treated with radiation. And thanks to all those ones, we can, as a society, treat some cancers, and people will not die of that condition. So they will probably live with cancer for many years, and then they can die either of cancer or of something else. So there are many ways in which this research is being carried out. So there are drugs and clinical trials. And I want to focus in cancer biology at the moment, because it's the area in which I contribute. And in cancer biology, what we do is that we study some cells, and then we can see, okay, those cells are being observed on the different conditions, and they will be healthy cells. And then cancer cells will have different characteristics. So instead of having one nucleus, they can have a different type of nuclei, or they can be, the boundaries could be more porous, or many other things. So we take these cells and we analyze them. Now the question can be, where do the cells come from? And this is a big part of my talk today, because I'm going to be speaking about one specific type of cells, and they are called HeLa cells. So these cells are probably the most important cells in cancer research and in many other areas of research. And HeLa comes from Henrietta Lacks. In 1951, a young mother in the United States was having some problems and had bleeding, and then she went to Johns Hopkins Hospital, and upon examination, the doctor discovered that she had a big tumor, and it was a really aggressive tumor. And then she was treated, and she died. So sadly, she died. She didn't live long after she was diagnosed. And here's where the story changes, and it becomes very interesting, that without her consent, some of the cells were taken and sent to a lab. At that time, it was not necessary to take consent from patients, but was still controversial. And her cells were changing the pattern of the whole world. So the cells of Henrietta Lacks really made a change. And I would recommend this book. It's called The Immortal Life of Henrietta Lacks, and very good chronicle of what happened with her cells and what happened with her family. It has been so influential that there is even now a film with Oprah Winfrey as Henrietta Lacks of what happened with her cells. So the cells went to labs, and at that time in the 1950s, it was not possible to keep cells living alive in labs, so they would die very quickly. But Henrietta's cells had a very different characteristic. So they started doubling, and they started doubling and doubling. This characteristic of cancerous cells that start doubling within every certain time. And they were so aggressively growing that they started generating them. Those cells are still alive today, and that is why the story is called The Immortal Life of Henrietta Lacks, and they're used everywhere in the world. So there are people who have done calculations of how many of these cells exist in the world, and someone did that if we would concatenate them all together, they can go from the Earth to the Moon and back with all these cells. So there are many cells, and they are used in many areas. So they can be observed with microscopes, and they would look something like this. So these are 4 examples of cells that came from Henrietta Lacks' tumor. So we use these cells. We use these cells and we observe them. And I have a collaboration with the Francis Crick Institute, where they are observing these cells, and they use an electron microscope. So what they do is that they scan the cells with an electron microscope, and then they thinly slice them and remove that slice. So they are destroying the sample, and then they again image the next part of the top of the tumor, and then they slice, and then they slice, and then they slice. So this is producing a 3-dimensional data set. So each of these regions here, that is one cell, that is one cell, that's another cell, one cell, and so on. And they don't move. So what we're doing is that we're looking down as these cells have been sliced. So what do we want to do? Well, we want to analyze these cells, and then those cells will be treated with the chemotherapy, and we see how much the chemotherapy affects these cells. So this is the kind of thing that we do. It's the first part of research into cancer, and then they will be treated in other cases, and then it goes to patients, clinical trials, and eventually, normally this process takes many years, they can be released as a chemotherapy or as a treatment for patients of cancer. So we take this as our starting point. So what is the task? So the cells have been acquired, they have been observed, and then I, as a computational scientist, I was given 2 tasks. The first one is to segment the nuclear envelope. So the cells will have the nucleus, nuclear envelope, and then they will have many parts. So we want to see the nuclear envelope because that's related to many conditions of disease. And then if we can destroy the nuclear envelope, we may be able to treat the cancer. And the second one was to remove, to segment the plasma membrane. Now, how do we do? There are many ways to do this. And basically there are three. One of them is I, as a human, can go observe and delineate it manually, which is very effective. So experts will do this and they can do it very well. This is what we consider gold standard. So if a very experienced person will do this, that could be one way of doing it. It's time consuming. So I've done it and it takes a long time to do this. Then we can do what computer scientists do, that is design algorithms to go segmenting them, or then we can use AI. We can feed information to a certain architecture and then we can do it. There's a fourth option, which I will not mention here, which is doing the manual delineation, but expanding it using an army of people doing this. And this is done by some of my colleagues. I will not touch that at the moment. So let's just go to some of the options. So manually, what do we do manually? We have our three-dimensional stack. We select one of the cells, then we just segment and take just that one cell that we want to analyze. And then we start delineating and going through the nuclear envelope. This is one of my colleagues doing that. And if you don't have enough scientists, you can recruit other people to help you. And in this case, we have the Mayor of London, Sadiq Khan, who visited the Crick Institute and had a go at segmenting the cells. So that is one option. It's useful, it's time consuming, it's error prone if you don't know exactly what you do, but it's one of the options. But it's so time consuming that if you want to do this in 100 cells, it will take ages. So what else we can do? Well, we can design algorithms, and this is what I call HI, so human intelligence. We have a certain skill to develop algorithms, and we can do that as well. So I'm going to explain quickly one of the algorithms that we use to define the nuclear envelope. So we take one of the cells as well, then we do some filtering, we remove the grainy part of the acquisition, then we detect the edges, so we detect where there are changes of intensity, and by detecting those changes of intensity, I can have all of the edges, so there's an edge here, and then we can see all of those edges. Once I have those edges, I can process them, and I can do something. So I can say, okay, instead of the edges, I want the other part, everything that is not an edge, and I call that superpixels. Now, some of those superpixels I don't really need, so all the small ones, and I discard all the small ones, I keep the large ones, and you can see that this is going towards what I want to do, that is the nucleus. And then I continue my process, and I keep only the central superpixel. So that is the problem nearly solved, and I have it here. Now, as always, the algorithms are not perfect, so I can see that there are small regions that were not properly captured. So I do some processing in 3 dimensions as a human user would do, and then I can select which areas I want to keep. So that is a problem solved with this algorithm. And this is a reconstruction of what I do. Now, let's do it with the artificial intelligence. So there are many architectures in artificial intelligence. This is a very dynamic field. So we tested a series of artificial intelligence options, so VGT, ResNet, Inception, and UNet, and we came with the following. So we compare them, and visually, this is the result. So let's zoom in a little bit, and we can see that this is the algorithm that was designed for human intelligence, and these are all the other ones, which are not as good. They are not very good, and in particular, this one is not very good, and we'll touch in a second into that. So we measure how good this is, and we use 2 measures of similarity, Jacquard index and accuracy. And this is the algorithm, and these are all the other options. So we can see that in terms of accuracy and in terms of Jacquard, we were on the top. And this was enough to start sending things for publication. Now, UNet has a very interesting result that in some of the cases, it was not very good. But suddenly these levels were much lower than the other ones. So what is going on there? We always have to observe our results and see what's going on. And here in this region, we could see that the difference were probably these little sparks, which are not good, but then we'll process that later. But as we went along, what was happening was that UNet was segmenting not just the central nucleus, but the other nuclei. So this was not like with like comparison. Okay, so that is not fair. Let's see what's going on. So we changed, I'm not having just the ground truth here, but taking the ground truth of all the other cells, and that pushes the results of unit higher up. Okay, but this is not very good, and we can still post-process unit. And if we improve that with a little bit of morphological operations, which again is not AI, but it's human intelligence, but let's merge the two together, we were able to improve the results of unit. And by doing that, we're pushing from the original with the corrected ground truth to the official one. Now this post-process, and the results are much better. So that is the accuracy, which is very close to our algorithm, in some places slightly above, in some places slightly below. And if we see the Jacquard similarly, in some cases slightly above, in some cases below. So let's call this a draw at the moment, in which the algorithms were providing more or less the same level of accuracy. Now, the first task was the nuclear envelope. The second task was the plasma membrane. And we did, again, some algorithms to obtain the plasma membrane. And we were obtaining quite a good segmentation. Not as good as the nuclear. So that is the nuclear. And this one were the errors of the algorithm. But this is a much more difficult task. So does that region belong to this cell or to that cell? I, as a human, I cannot tell you. So it's difficult to know how good this is, because this is very difficult to know that part to which of the two cells belongs. Now, these are the final results in other cells, only with the design algorithm, so not the AI. And we can see that the resolution is exquisite. So we can have a very, very good segmentation algorithm. So these are the results. Two cells, that will be the nucleus, that will be the plasma membrane. And we can see this is where biologists take part. So I finished as a computer scientist, and I show them this is smooth, that's wrinkly, and that may be due to some biological parts that I'm not absolutely sure about. So that is biology. I'm a computer scientist. I finish here my result, and then my colleagues will continue with this research. So just to finish, all these papers that we publish, we make them open access so everyone could read them. And not only that, we also publish our data so anyone can download the data and use it for an experiment. And we publish our code so everyone can get the code and compare the results. And with that, I'm finished my presentation, not without first giving acknowledgements. And the first and most important acknowledgement is to Henrietta Lacks, because she, without knowing, she donated the cells that have been used in so much research. And then this is my current team, so I didn't do this work alone. Most of this work is from my previous PhD student, Shefar Karabakh, who finished his PhD last year. And then my colleagues at the Crick Institute are Martin Jones and Lucy Collinson, who did all the acquisition. And with that, I finish. There's time for questions, but I think we'll pass to the next speaker, and the questions will be at the end. So thank you for listening, and I'm going to stop at this moment.
Okay, thank you very much, Carlos. Very interesting. Just answering, just in case, yes, the slides and recording would be available after the event. Thank you. Just some people actually have been asking about that. And also, please just post your questions and answer in the question and answer button at the bottom of the screen. Don't worry if you can only see yours or you cannot see others, because this is for safety, security, and reasons. But the panelists are seeing your questions and answers, and they will, respond to them at the end of the last talk. So we thought, just it was just a little thing. So Cristina, it's yours.
So I'm just trying to find the camera for me. Give me 1 sec. Camera, there we are. Okay, found it. Thank you. So now hopefully you can see my screen, okay? Yes?
Yeah. Yes.
Okay, thanks, guys. Okay, so thank you very much for the invitation, Ed, and everyone in computer science. I am from the School of Health Sciences. I am a radiographer by background. So like Carlos brought in the human intelligence in AI, I think I would like to bring in the person-centered care in AI and what we do in radiography. So it's important to acknowledge the AI ecosystem of medical imaging. On the left-hand side, you can see here the people who are closer to the patients when they're doing the scans or examinations in medical imaging are indeed the radiographers. There are also those who prepare the imaging parameters on the scanner, position the patients, and make sure they are okay throughout the scan. On the right-hand side, you can see the people who sit behind screens and look at the results produced by radiographers. And these are the medics, and they're called radiologists. On the top, on the bottom right, you can see computer scientists who work with numbers and coding to optimize processes in medical imaging. On the left-hand side, physicists who work a lot in optimizing the imaging examination in terms of the physics principles. In the middle, you can see the engineers who work a lot around the engineering of the scanners and the equipment in medical imaging. So it's quite a big ecosystem. And on top of that, it takes a lot of workflow optimization, which is done by the radiology managers who work alongside all of these professionals to ensure a smooth service delivery in clinical practice. AI has been around for many years. So you guys, computer science, you have been working for ages on it, or on your labs, on the science benches, but it wasn't visible to us until very recently in clinical practice and imaging. So that's not surprising that the publications in this area for medical imaging and AI went up since 2010 in an exponential growth, really. What has accelerated for us the integration of AI in healthcare is, of course, the increase of the computational power and development, the big data availability from across the clinical settings, and digitization of healthcare, which is currently underway. And of course, the research in neuroscience and computing that allowed us to transfer the knowledge from how the brain learns, the human brain, into how machines can learn. There are different tasks of artificial intelligence in biomedical image analysis and beyond imaging, so like image enhancement, detection, segmentation, tracking, quantification, classification, visualization, analytics, modeling. So there is much more than reporting of images, which happens on the majority of the AI applications currently. And within radiography, beyond the reporting of images to get a diagnosis for a patient before they start their treatment, our roles are really operational in terms of the AI tools. So they might include vetting and ID confirmation. So they might include planning, protocol selection, pilot images, slice positioning to get the optimal imaging planes, volume planning, contrast injections, and then in the acquisition to optimize the acquisition parameters for optimal image quality, contrast, resolution, signal to noise ratio, dose reduction when there is dose involved like CT, X-rays, scan time reduction for the patient's benefit and comfort, quality assurance of the equipment, and of course post-processing. Very often we do some light post-processing before going into the radiologist for diagnosis. Then we have, of course, different roles from radiography workflows into image production to image interpretation in the UK. Many of the radiographers do image interpretation, image segmentation, registration, and of course, for precision medicine, contributing to the workflow of precision medicine. Medical imaging has not been unanimously affected in terms of the AI progress through the ranks of the different modalities, or indeed the different brain organs, the different organs of the body. So MRI and CT, what we call cross-sectional imaging, seem to monopolize at the moment the AI applications because they are much more computerized techniques of medical imaging, followed very closely by ultrasound, and then X-rays and other techniques like SPECT, CT, or similar. Also, in terms of the organs of the body that really have seen an increase of AI applications is the brain, the cell, like Carlos has shown, and then it's all the organs that are subject to screening, where actually big data is produced, like lung screening, breast screening, etc. And of course, heart, eye, and chest further down. And now with COVID-19, the chest has gone massively up in terms of the applications for AI tools. For us clinicians, I mean, for you guys in computer science, many of the things we discuss in conferences seem to be common sense. But if a clinician goes first time in an AI conference, they will be faced with a jargon, or like my little daughter says, jungle. So it isn't a jungle, it's a beast we have to know. It's a whole new language, a brand new world for radiographers and all of the clinical practitioners in the AI ecosystem. So we need to understand what an algorithm is, a training data set, a validation data set, a test data set, what's a training loop, What are these hyperparameters? Sound very threatening. Examples, loss, optimization functions. So all of these things we need to understand. We need to understand for the basic applications, not for how an algorithm is being constructed or done, but to understand how it works in our practice. Not just to know these words to understand, but also to be able to explain, because we are patient facing. So someone might ask, so why is this coming earlier? How is this result being interpreted? What does it mean to have a machine to interpret my results on top of a clinician, for instance? Is it better? Is it worse? So we have to be able to help our patients understand how the integration happens and what it means for them and for their care. The key issues in radiography and radiology include clinical validation, adoption and implementation of AI, the lack of unanimously accepted at the moment regulatory standards and frameworks for AI tools, because there are so many out there which are not validated or properly accepted or regulated or accredited. So we need to know, because we will be procuring in the future alongside our clinical colleagues, radiologists, the AI tools. So we need to know what is acceptable and quality or not. And we will be doing QA or quality assurance to ensure they work okay on a day-to-day basis. And then there is ethics and accountability in the case of erroneous interpretation or erroneous use of AI techniques. And of course, very importantly, alongside all of this adoption is the training of practitioners who work in AI, and they are not computer scientists who know things inside out, really. So when it comes to adoption, it's important to ensure also patient acceptability and trust for these new techniques, person-centeredness, explainability of AI, so it's not a black box for us, and of course, in the future, careers and roles within that ecosystem. So we have been slow as a profession, I have to admit, to understand what AI might mean for us, for the patients, for the practice we perform, either clinical, either educational research, but we're now making some progress. We have organized some conferences and webinars, and I'm very pleased that I'm here today, because this is part of this awareness for our discipline. We have created practice guidance, which I'm presenting at the end, about education, research, partnerships, and of course, clinical practice. We have conducted some surveys to try and make sense on what AI means for us, how much we understand or not, how many skills we need to develop or not, what are our perceptions and expectations for the future. We try to work with regulators like BSI to contribute to the ongoing work about regulatory frameworks. I'm indeed part of the BSI Standards Institute for creating a framework for AI validation in healthcare in general. We have created more partnerships with AXREM, which is an organization, a consortium of manufacturers, with NHSX and with industry. And we are trying to create some short courses as introductory courses into AI and data sciences. I know City has an amazing AI Masters that Ed is the program director. Is that correct, Ed? Yes? So we are trying to create something to bridge in the gap with that Masters. And of course, there are things from Health Education England, like online courses, other HIs. But we don't get to do enough original research, and most importantly, prospective research. Most of the data, we have published a study on AI and cardiomegaly. Most of the data people now use at the moment are retrospectively acquired data. We have run a conference last year to raise awareness with the British Institute of Radiology called Radiography 2020, where we invited clinicians, academics, researchers, manufacturers to present. So this was part of the awareness raising for a smoother AI adoption, and to try to convince people to engage with AI and not be afraid of it. And we learn a lot from our colleagues, the medics in radiology, where they try to apply new learnings into their AI, into their curriculum with AI learning. So they have produced white papers and guidance and some training suggestions. So the new curricula should include knowledge capture, not knowledge retention. There should be collaboration with and management of AI applications, perhaps a better understanding of probabilities and how to apply them meaningfully in clinical decision-making, in particular when it comes to patient care and treatment. And of course, very importantly, what I said at the beginning, person-centered care requires the cultivation of empathy and compassion. We cannot have AI without this element in clinical practice. We need both sides of precision medicine, and person-centered care is vital, at the same sense that human intelligence is vital, like Carlos expected. And working with everyone is really important, with the patients, with the clinical practitioners who face the clinical challenges that needs a solution, with industry, professional bodies, institutions, disciplines, including computer science and physics, and have a national plan for AI research in healthcare. So we have had different ideas how to integrate AI in the radiography curriculum. This could run as workshops or introductory modules as we're doing, intercalate as in medicine, and of course work with our computer science colleagues to co-create courses. Furthermore, encourage students to engage in dissertation projects across the disciplines, supervise PhD AI research, which we're trying to do, raise awareness, and this will evolve further, hopefully with more ideas and more practice in the future. We have to be very close to our profession in terms of the values we have, which are around patient safety, image quality, patient care. And also, this is from a word cloud from one of my students. And when I asked them what is really valuable for you as a radiographer, is helping others. That came out very, very strongly on the word cloud. So it's important to ensure that we address these things as we move forward into the digitalized healthcare and precision medicine ecosystem. And we should never forget that for clinical practitioners, although AI really goes through the ranks very quickly, there is no substitute to the human touch in clinical practice. And whereas a very advanced AI tool might bring you amazing results, how these are communicated to you and who tells you what is important. There are many different academic topics for radiography. I'm not going to go further into those. They might relate to ethics or validation. But what is more important is to ensure that we do have patient-centered care in the era of AI, and we ensure that with the help of an AI tool, we customize the examination for every patient. These are some of the courses we have at City. On the right-hand side, you can see the MSc Artificial Intelligence that Ed is leading on. And we also have on the left and bottom 2 modules as part of our postgraduate program, which can serve as an introduction or as an adjunct to that. The introduction to AI for radiographers, which gives them a light touch of AI, and people from computer science contribute to that, which I'm very helpful. So Giacomo contributes to that. Thanks for that, Giacomo. And of course, we have the other side of AI, the patient-centered care module in medical imaging, when we speak about empathy and patient and service user needs in the medical imaging environment, including customization of care for these patients and service users. There are many opinion pieces out there at the moment for radiography, talking about where we are, what does the future hold, what are we moving forward. There are also many surveys on AI for the workforce, for clinical practitioners. The UK one has just been accepted for publication in Frontiers Digital Health. And what we found out was not striking, but quite alarming, that women, older professionals, and those without advanced degrees are much less confident in the use of AI. And this has implications for the workforce, for the training, and also for the adoption of AI in healthcare. I was very disappointed, but naturally not surprised by this outcome. And last but not least, we have created some guidance, which is the first of its kind on AI for the UK, which is now being taken up by the European body, the European Federation of Radiography Societies in different countries across 110,000 radiographers in Europe, to try and create a framework for adoption of AI in medical imaging, in particular radiography. And this relates to education, to clinical practice, to research, and reinforces the need of some really important partnerships in radiography and medical imaging. Looking onto the future, what will be important for the integration will be co-production with patients. We cannot do anything for them without them. Very strong and seamless clinical academic industry partnerships. And when it comes to partnerships in academia, we need to include all of the ecosystem. So radiographers, radiologists, physicists, computer scientists, nurses, everyone who works within the system work hand in hand to deliver seamless person-centered care. And just use AI. Please don't forget that AI in medical imaging is so much more than diagnosis. It's so much of the operational aspects, like positioning or preparing for the scan, or planning for the scan, or post-processing. So please do remember, let's all of us remember that this is a huge aspect of AI in medical imaging. Thank you very much, and I'm happy to answer any questions at the end.
Thank you very much, Christina. Very interesting. So Giacomo, your turn.
Yeah, hello everyone. Let me share my screen. Are you guys seeing the slides?
Yes.
Okay, great. Okay, sorry. Hello everyone. It's really a pleasure for me to be a speaker in this webinar. So also thanks to the organizers for the invitation. My name is Giacomo Tarroni. I'm a lecturer in AI. And the title of today's talk will be Learning to Tell Wrong from Right. And it will be about ways for detecting anomalies in medical images without expert supervision. But let me first quickly introduce the research center that I'm part of at CT. The center is called CTAI, and it currently consists of 24 members, among academics like myself and Eduardo, who's the director of the center, PhD students, and RAs. The center's research spans a wide variety of topics relative to fundamental and applied AI, artificial general intelligence, and explainable AI. And it has also an interest in legal and ethical challenges of AI and its socioeconomic impact. Finally, as said also by Christina, it runs the MSc in Artificial Intelligence in the Department of Computer Science at CT. CTI has currently several ongoing projects focused on healthcare. One of these is unsupervised anomaly detection for medical images, which is my main area of research nowadays, and also the topic of this talk. Some of the other projects that I lead on are federated learning for medical image processing and quality control and motion correction for cardiac MR images. Other colleagues from the center focus on brain connectivity analysis for ADHD detection using fMRI images, detection of COVID-19 using CT scans, reward devaluation modeling in autistic children and adolescents, and also MRS brain tissue imaging for tumors evaluation. So if any of you is interested in any of the above, or would generally like to know more about the center, please feel free to reach out to me or also to Eduardo, of course. Now, I'm sure that many of you have seen in the past few years, many headlines like this from Time magazine that says Google's AI bested doctors in detecting breast cancer in mammograms. And if you were to read the article, you would find remarks like this quote, saying that the AI system outperformed all of the human readers. This is another example from The Verge, titled DeepMind's AI can detect over 50 AI diseases as accurately as a doctor. And there's a quote there saying that performance reaches or exceeds that of experts. So now, if you, despite these rather sensationalist, I would say, press articles, both of the research works behind these articles was actually very remarkable. But if you were to dig further into the method section of the relative scientific papers, of course, you would notice that quite a lot of data collection and labeling had to happen to build these AIs. In fact, for breast cancer detection, the AI was trained and tuned on mammograms from 76,000 women, which is a lot. And to generate the labels that were necessary for training and evaluating these AI, radiologists needed to provide reports for each of these subjects. And biopsies were also required in, I think, more than 1,000 cases. In addition, lesions were localized and manually annotated in more than 7,000 images. And similarly, for the AI imaging application, the AI was trained on almost 15,000 scans. And for each of these scans, the ophthalmologist had to generate detailed reports. And in addition, almost 900 scans had to be manually segmented. So, but what does this mean in practice? So for the mammograms, and you can see an example in this slide, this meant for radiologists to see through thousands of images and manually localize and classify potential lesions. For eye imaging, here you can see the required pixel-wise segmentation maps that experts needed to produce in roughly 900 images to essentially highlight the different anatomical structures that are present in the scan. And all of these annotations and written labels were required for the fully supervised training of these AIs in order to get such high performance levels. And I think that from just these two examples, you can rather easily see what are the main limitations of these fully supervised approaches. So first, they need very large data sets with many pathological cases. And this can be very difficult to come by in many cases, also for privacy-related reasons, among others. And it's also, generally speaking, very expensive. Second, images need to be annotated by experts, often as we've seen at the pixel level. And this is also a very strong limitation because experts are few and they're generally difficult to enroll in these studies. Third, they can detect only pathologies present in the training set. And this is also a very strong limitation because we know that some diseases are extremely rare, so it's impossible to get a sufficient number of training images for them. And in addition, many diseases are still unknown. But is there a way to bypass these limitations? Well, this is in a way the promise of unsupervised learning. Unsupervised learning is a branch of machine learning that specifically focuses on training models without strong annotations. In the field of anomaly detection, it enables very promising approaches to tackle each of the previous limitations. First, it needs very large data sets, yes, but with only normal cases, which are much easier to collect. Second, images do not need to be annotated by experts. And third, it can detect previously unknown pathologies as well. And this, of course, sounds great, and it sounds almost too good to be true. So let's see how this can work more in detail. So the overall idea of unsupervised anomaly detection is to use only a set of images from normal subjects for training a model, and then to use this model to then detect and localize anomalies on test images. If you think about it, this is actually somewhat similar to how radiologists read the scans. And in fact, there are several studies that show that even unexperienced interpreters, like normal people, can become rather effective at detecting anomalies if they've been exposed to a reasonably large data set of normal images. This approach has several potential applications, first detecting and localizing pathology, we're talking about it now, but also discovering unknown pathology. And it can also work as quality control tool to detect images that have been wrongly acquired or images with unwanted artifacts. And this is also a very important aspect, as Christina just mentioned. There are many different approaches for unsupervised anomaly detection, including density-based methods, self-supervised methods, and reconstruction or restoration-based ones. And I will focus on these last two approaches, which have proven to be the most promising as of late. Now, let's start from a self-supervised method called foreign patch interpolation, or FPI for short. This method essentially leverages the natural variations in normal anatomy that is available in the training dataset to create a range of synthetic abnormalities. Specifically, imagine you have two independent normal images, A and B in the slide. Then two identical patch regions are extracted from each of them and interpolated using a factor alpha, therefore creating a new patch. This new patch is replaced in image A in order to generate an interpolated image. The interpolation factor alpha, the patch size, and the patch location are all randomly sampled from uniform distributions. Here you can see an example of this interpolation process, and you can see the generated interpolated image in the middle, also with the synthetic anomaly roughly in the center of the scan. A dataset of interpolated images is then created using this strategy, and it's used to train in a fully supervised fashion at this point. So as the other methods that I mentioned, a common segmentation neural network to localize the patches and estimate the interpolation factor alpha. FPI has proven to be remarkably successful in the medical auto-distribution challenge held last year at MICCAI, both in the detection and in the localization task of anomalies in both the brain MR and abdominal CT images. However, a limitation of this method is that it relies on the patch interpolation mechanism to generate anomalies, and therefore is likely to fail in detecting anomalies that cannot be simulated by it. Generally speaking, these methods sort of tend to shift the problem of identifying unseen anomalies to that of generating them, which is not necessarily easier. Instead, reconstruction-based methods aim at using generative models to learn the so-called normative distribution in the data, which means the distribution of the normal images. The most common setting consists in using an autoencoder network, like the one that you see here exemplified in the slide, to learn to accurately reconstruct images from normal subjects. Because of this, at test time, if an image with an anomaly is fed to the network should be unable to reconstruct the anomaly and should generate instead an anomaly-free version. The anomaly could then be identified and localized by essentially simply subtracting the reconstructed image to the original one, as you see here at the bottom right of the slide. This can be considered a more principled approach, and it has been very popular since 2018 with more than 20 architectures using autoencoders, variational autoencoders, GANs, and hybrid models with these other architectures that were presented in the literature. The main limitation is that they have shown relatively low accuracy. And one of the main issues is that despite not having been trained on them, the generative models are powerful enough to reconstruct the anomalies too. And you can see an example of this in this slide with a reconstruction at the top right pane that still shows some of these hyper-intense anomalies that are present in the input image. So of course, when you were to subtract this to the original one, you would miss those. To try to solve this limitation, restoration-based methods have been recently proposed. These methods follow a very similar network design, but they try to actively modify the input image, usually using gradient ascent techniques, in order to create a restored, anomaly-free version of it. This is usually obtained through an iterative process that you see here at the bottom right of the slide. And the final, hopefully at that point, anomaly-free image is then subtracted as before to the original input to locate the potential anomalies. This method has shown an accuracy substantially improved in most cases, but this remains still relatively low. And in addition, these methods are limited by computing time, which is now around 80 seconds per image versus 0.1 seconds for the reference reconstruction-based method. And in addition, these methods commonly use convolutional neural network or CNNs architectures, which cannot easily digest the original big size and high resolution of most medical images. Now let's briefly change subject and focus for a moment on implicit field learning. Implicit field learning has been very recently introduced, and it essentially allows the reconstruction of high-resolution 3D shapes, like the rabbit that you see in this slide, through learning their implicit surface representation without the need for convolutional neural networks. Sergio Navalmarimont, who is now a PhD student at CTAI under my supervision, recently had the brilliant idea of essentially repurposing implicit field learning for unsupervised anomaly detection. In a nutshell, his approach features an auto-decoder architecture that learns an embedding, so a code for each of the normal samples in the training dataset. And all of these codes are learned and stored essentially in the matrix that you see at the center of the slide. At test time, an optimization procedure identifies the embedding that best describes the test image. The implicit field network can then be interrogated by providing a set of special coordinates, X, Y, and Z, that you see here in pink, in order to retrieve the predicted intensity values and thus generate the restored image. Since it doesn't involve CNNs, this approach natively handles high-resolution medical images in 3D at very low computational costs, and this is quite remarkable. But importantly, it greatly outperformed the previous reconstruction and restoration-based approaches with around 15 dice improvement against the best competitor. In the two examples on the left, you can see that implicit field learning here, dubbed IF, especially in its native 3D implementation, so the rightmost column, can be much more accurate in identifying anomalies in brain MR images when compared to other methods. And here, just to guide you, the pink is the predicted anomaly from this method, and the black is the ground truth. This method was recently accepted for presentation at the upcoming MICCAI 2021 conference. And in the future, we plan to thoroughly test it using other data sets and also other imaging modalities. So in conclusion, here are some take-home messages on anomaly detection in medical images. Fully supervised approaches are powerful, but limited by the availability of data, experts, and knowledge of pathology. Unsupervised approaches bypassing these limitations are possible, and they are currently a very exciting area of research, but well, there is still quite a long way to go. Thank you very much for your attention, and happy to take questions later in the panel. Thank you.
Thank you very much, Giacomo. Great. So we have, sadly, little time left, and we have some questions in the panel. So what I would suggest is at least to have, one participant and responding one of the questions in the panel, starting with Carlos, then Cristina, then Giacomo. If we have more time left, we can actually proceed, with the same kind of procedure. Nevertheless, please, the participants, now the speakers, you have, listen to them, and as said, the slides and the recording will be available. You have their contact details. Otherwise, just Google their names, and you can, take it from there. Okay. So, Carlos, would you like to pick up one particular question from the?
There was one particular question asking about the accuracy of AI and if there was a point in using some post-processing, and in our application at least, yes. So what we found is that our initial results of the unit were not very good, but if we changed them and we did some post-processing using traditional morphology methods, we were able to improve these ones. So that may be showing that a merger between techniques can improve the results that you can obtain. It may be different in other cases, but yes, in this case, merging techniques could be a useful thing to do.
Okay, thank you. Cristina, you fancy to pick up one?
Yes, thank you. I have answered some questions in writing, so they are in the answered one, but if I can pick two very quickly. One is from Alan Calvert, which asks about the ethical aspects of liability and accountability of AI algorithms when they don't work well, I presume. So I guess, Alan, the field is not very clear yet, but there might be joint accountability if an AI algorithm doesn't really do what it promises, like the validity and reliability of the algorithm. So for instance, it might lie on the clinical setting that uses that, like the hospital. It might lie with a clinician that also applies it in practice, and also with a company that produces it. It's not quite clear yet, the legal framework around it. And I know that in the EU, very recently, I think in the summer, in June 2021, there has been a regulatory framework out there discussing liability. So that's Alan. And very quickly, Ed, if you allow me, the other one is
Absolutely.
very quick.
Yep.
From Adonio Euleteri. So he asks about, he says that reviewing AI papers, his experience has been abysmal, and he sees many issues about distinct lack of knowledge of fundamental theoretical understanding, and there are no calibration measures. Yes, I agree. And Antonio, you might know that recently a consortium of clinicians, computer scientists, AI experts have come together to produce some guidelines, the Consort and Spirit AI guidelines for writing AI papers in relation to AI technology, because exactly of that lack of standardization of how to write. There is a lot of cannibalism, how people write papers at the moment. So hopefully this Consort and Spirit AI guidelines for writing AI papers and research can help with standardizing and offer some structure in how we report AI tools, in particular about the methodology. I can share those as a link. I'm going to try and find them. Thank you very much.
Thank you, Cristina. Giacomo?
Yeah, I can try and answer I've just seen Esther's question. Actually, there's some more later on. So an in-house question from Esther, who's also an academic in CTAI. So she refers to the use of post-hoc explainability techniques in these methods, and why they're not seen more often in our research, for instance. So I have nothing against them, of course, like SHAP of Lyme, they're quite well known. It really depends on the type of application that you're after. If you're closer, let's say, to the translational threshold in which your work is actually to be picked up, at least hypothetically, for an actual application, then these sort of techniques would become more important. If you're more towards the developing an algorithm just to see what's the accuracy that you can get, hopefully using good statistical analysis, as mentioned before, I would say it's not that crucial. For my specific application, what I talked about, the restoration-based methods have an explainability sort of outcome directly from the method, because you generate a restored image. So you can always tell the doctor, look, this is what we think would be the equivalent normal case. So giving to the radiologist a chance to see what actually triggered that localization, which is just a subtraction between two images, to me already counts like explaining quite a lot. But generally speaking, of course, I have nothing against what you suggested. Let me quickly read these new questions. Similar, so one about implicit learning, similar to transfer learning. So no, they're very different things. Transfer learning means that you take essentially a network that was trained on one task, on one data set. Imagine in classifying images of dogs, cats, boats, and cars. And you use that trained model to then do the same classification in another data set. And usually you fine tune your network on your own data set, which might, for instance, feature only dogs and cats. Implicit field learning is really a 3D shape reconstruction method that moves away from the most common approaches to represent high resolution shapes. So you can represent 3D shapes with voxel methods, in which you have a voxel, so a 3D pixel essentially for your image. You can use point clouds, you can use meshes. Implicit field learning tries to essentially predict the classification of pixels inside or outside the boundary of the shape you're trying to reconstruct. So they're relatively different things. There's also another question, unless there are some other questions for the others, Ed. I don't want to...
Carlos, you have only answered one question.
Yeah, exactly.
A couple of minutes. You want to answer quickly another question?
I was asked about it's related to what Giacomo was saying, what training we did. So we did have some of that transfer learning. So we use some pre-trained networks, but in some cases we use training from scratch. So for the unit, we did everything from the beginning. We generated our own patches of labels, and we generated our own, we use some expert segmentation to generate the training for the unit. And I was asked about the data. So our data is a very high resolution data. So it's 8,000 pixels by 8,000 pixels by 500 slices. So it's heavy. And then the individual cells, when we were doing just one cell, was a box of 2,000 by 2,000 by 300. So it's still quite a large data set, much larger than the normal image classifying, as Giacomo was saying, cats and dogs. There will be smaller data sets. So that was not a question.
Okay. So unfortunately, we're running out of time. Okay. As said, please keep on with this conversation offline. All the participants have the details of the speakers. I think that has been great. So I would like to thank, obviously, the participants. I would like to especially, thank the speakers, Cristina, Carlos, Giacomo, Stephen as the main organizer, and last but not least, Lucy Bennett, who has been, taking care of the technical side of things. So Stephen, you want to say one final word before we close the event?
Yes, just thank you as the chair, thank all the speakers, thank for everybody who's turned up and made the meeting an interesting one with very good questions. And I would just remind you that the next meeting is on the 11th of November, and it is Technology Challenges in Healthcare. Thank you all very much.
Thank you, Stephen.
Thank you, everyone.
Bye, thank you.
Thank you for your attention.
Bye.